We're back with going over the review problems for this playlist for Unit 4. As always, you should read the question on the first slide and then work it yourself. Pause the video if you need to before going on to the next one to work it yourself and then check it. In the last video, we did the first 6 problems, and this one we'll do the next 6, 7 through 12. These problems are matched very closely with my practice test problems, which are matched pretty closely with the exam problems. Okay, so see if you can do this. When do we use a confidence interval, and when do we perform a hypothesis test? How do we know when to use a left-tailed, right-tailed, or two-tailed test? How do we know when to use a one-sample or two-sample test? What about when we have paired data? So see if you can write a couple sentences about each of these. Press pause now. It's important that you work these out yourself. Confidence intervals are used to give an interval estimate of an unknown population parameter. Hypothesis tests are used to test if a sample is likely from a hypothesized population or 2 samples are likely from the same population. Often we perform both of these together. We use a left-tailed test when we want to show a sample is from a population with a parameter less than the hypothesized parameter. We use a right-tailed test when we want to show a sample is from a population with a parameter greater than the hypothesized parameter. We use a two-tailed test when we want to show the sample is from a population with a parameter different than the hypothesized parameter. How do we know when to use a one-sample or two-sample test? We use a one-sample test when we want to test a single sample statistic against an assumed population parameter. We use a two-sample test to test 2 sample statistics against each other from 2 independent samples. Paired data, for example, before and after data, is really just one sample of ordered pairs. So what we do is find the difference in each of those pairs, and now we have a one-sample situation. So we perform a one-sample test on the differences of each pair when we have before and after data. When do we use each of the following? Z-test, T-test, hypergeometric proportions test, binomial proportions test, proportions Z-test, a chi-square test, and an F-test. And notice the ones that are starred have built-in calculator programs on the TI calculators, and I have provided TID4 programs for the other ones. But one of the things you got to know is which one's going to work, right? Which one to use, which one to choose. So see if you can answer these questions now. Press pause. On a Z-test, we are testing means. The distribution of sample means must be approximately normal, and the population standard deviation is known. Same thing for a Z-interval. A T-test or T-interval, we're testing means. The distribution of sample means is approximately normal, and the population standard deviation is unknown. So when the standard deviation is known, we're in the Z-test situation. The standard deviation is unknown for the population, then it's in a T-test situation. Most tested proportions are actually describing a situation that should properly be done with a hypergeometric distribution for computing probabilities and inverse probabilities, because sampling is typically done without replacement, and even though the population size may sometimes be large, it is finite. So that's exactly what's used for a hypergeometric proportions test. We're testing proportions, the population size is known. Especially we have to do this if the population size n is relatively small, capital N. And sampling is done without replacement. We can use binomial distributions to approximate these hypergeometric probabilities when we're doing proportions testing in confidence intervals. It's appropriate when we're testing proportions and the sampling is with replacement or as an infinite population size. But it works well as an approximation if you're sampling with replacement if the population size is relatively large and unknown. So the nice thing about the binomial proportions test, you do not have to know the population size. But if you're reasonably sure it's big, then it's going to be producing essentially the same results as the hypergeometric. The proportion, the Z-test, one proportion Z-test, actually all these have 1 and 2 proportion versions, or 1 or 2 sample versions. But the 1 proportion or 2 proportion Z-test, we're testing proportions. Now really we should use a binomial if the population size is unknown, or hypergeometric if the population size is known. But it works well as an approximation if the population size is large and the sample size is also relatively large, if both NP and NQ are greater than 30. The chi-square test for variances or standard deviations is used in a one-sample situation where we're testing variances. In this case, the distribution of individual values must be normal, okay, or at least very, very close to it. The F-test is the two-sample version of that, where we're testing variances or standard deviations from two samples against each other. The distribution of individual data must be normal. So the ones with the asterisks have calculator wizard programs for those tests, and all the rest of them I have programs for. So let's go ahead and summarize this just a bit more. So here's a decision chart. The inferences about the means, then we're going to, the ones that we've done, all the sample means have to be approximately normal. If they're not, then you have to use some non-parametric methods that we haven't studied yet this semester. Population standard deviation is known, then we're going to be using the Z distribution, or standard normal distribution. If the population standard deviation is unknown, we'll be using a T distribution. So when the population standard deviation is known, we're doing a one sample confidence interval, we use the Z interval app. One sample hypothesis test, use the Z test app. If it's paired data, and we're doing a hypothesis test, or interval for that matter, we use the differences and use the Z-test app or the Z-interval app. If it's a two-sample hypothesis test and interval, use the two-sample Z-test and the two-sample Z-interval. I don't think in my homework problems or my exams we ever use those two at all. If the population standard deviation is unknown, then we replace the Z with a T, and we replace sigma with S, basically, and it becomes a T distribution. For a one-sample confidence interval, use the T-interval app. For a one-sample hypothesis test, use the T-test app. If you have paired data, and we're doing a hypothesis test, do the differences in the two, and just run a regular T-test or T-interval as appropriate. For two-sample hypothesis test interval, you can use the two-sample T-test and two-sample T-interval apps. Inferences about proportions. Well, if it's a one-sample hypothesis test, if you'll just use my one purport program, it will run the hypothesis test correctly on that. The last value given will be the best value, which will either be a hypergeometric if the population size is known, or a binomial approximation if it's not. It also reports what you would get from a one proportion Z-test as well on the calculator, which is a normal approximation, but that one is really not the appropriate one. A one sample confidence interval, we'll use the one proportion Z interval app, but that's only appropriate if both the population and sample sizes are large. Say NP and NQ are both greater than 30. For two-sample hypothesis test, if the population and sample sizes are large, we can use a two-proportion Z-test. And again, you need both N1P1, N2P1, N2P2, N1P, I'll say it right, N1P1, N1Q1, N2P2, and N2Q2, all of the NPs and NQs, all four of them, to be bigger than 30 to make this be reasonably sure you're going to get a pretty good p-values that are close to where they should be. So the two-sample confidence interval version of that is the two-prop z interval, two-proportion z interval. Inferences about proportions and means are extremely common. A little less common would be inferences about standard deviations, but they are important if you're trying to see if the variability is different. So a one-sample confidence interval and hypothesis test, if the individuals are normal, would be that my ZTests, standard deviation test program. Notice you do have to check the individuals are normal, not just the distribution of sample means. So you would probably need to do a normal probability plot for that. A two-sample hypothesis test, if the individuals are normal, use a normal probability plot to determine that, would be the F test, which is built in the calculator. The two-sample confidence interval version is an F interval, which I have a program for that one on a TI-84. So let's try an example here where we need to find a sample size. Suppose that we want to construct a 95% confidence interval for the mean amount spent on college textbooks at UAFS this year. How we would like the margin of error to be no more than $20. Suppose that we know that the standard deviation of all such annual textbook purchases is $40. What's the minimum sample size we need for a survey, and what kind of test do we need to use? Press pause now. Since the population standard deviation is known, that's kind of unrealistic, and we are constructing a confidence interval for a mean, the appropriate type of a confidence interval is a Z interval. Okay, hopefully you realize that we're testing proportions. Since the population standard deviation is known, we're constructing a confidence interval for a mean. And the appropriate, we're testing, I said proportions, we're testing means here. The appropriate type of confidence interval is a Z interval. And we can do this to find the N, we need to use this formula right here. N is greater than sigma times the inverse norm of 1 minus alpha over 2, or 1 plus confidence level divided by 2, which is the way I did it here, from a standard normal, 0, 1, divided by the margin of error. Square that, and that gives us a number which we always round up to the next whole number. So here you can see it worked out by details. But if you have my program, N4CI4MU, the N, sample size, for a confidence interval for a mean, mu, then you can run that, and it tells you it computes the sample size for a confidence interval for mu. And it actually does this with an iterative process with a sample, with a guess at the standard deviation for a t distribution. But for a z, it will do just exactly what this formula is doing right here. So we do that. It says give us a confidence level. We tell it 0.95 in this case. Give us a margin of error. We said 20. Population standard deviation is known, so we select that, put it in, which is 40, and the minimum in, it tells us, is 16. Now this works if the data is approximately normal, or at least if the distribution of sample means is approximately normal. Well, when would that happen? If the data is pretty close to normal, a smaller sample size is fine. So if it's not highly non-normal, 16 may work, but otherwise we would probably go up to 30. But homework problems or exam problems are probably looking for the 16 here. Next, a research journal reports a 95% confidence interval, a T interval, for the mean time spent studying for final exams at a university to be 15 hours to 21 hours. They report surveying 50 students. Can we work backwards from this confidence interval and find the sample mean, margin of error, standard error of the mean, and the sample standard deviation? The answer is yes, we can. Can you do it? Let's see. Press pause now. Well, the first thing to remember is the x bar value is going to be exactly at the midpoint of the interval, halfway between these two numbers. Well, the way to find that is to just average them, add them up, divide by 2. 21 plus 15 divided by 2 turns out to be 18. Notice 15 to 18 is 3, and 18 to 21 is 3. So 18 hours was the sample mean. The margin of error. Well, the length of the interval is twice the margin of error. So if we take the length of the interval, we can find by subtracting. If we divide by 2, we get the margin of error. So 21 minus 15 divided by 2 is 3 hours. That's the margin of error. And again, x bar plus 3 is the top one, 21, and x bar minus 3 is the bottom one, 15. What's the approximate standard error of the mean? The standard error of the mean is, another name for that is sigma sub x bar, which is what it really is. It's the standard deviation of the x bar values. Now remember, here is our formula. The margin of error is the S, the standard deviation of the sample, divided by square root of n, times inverse t, 1 minus alpha over 2, or if you'd rather write that, 1 plus confidence level over 2, and then degrees of freedom, which are n minus 1. Okay, well, the standard error is the standard deviation of the x bar values, which is approximately this, well, it's exactly the sigma of the population, the standard deviation of the population divided by the square root of the sample size. We don't know sigma, but we do know S, so it's approximately S over square root of n. Well, taking this formula at the top and solving for S over square root of n, we're just taking that e and divided by this inverse t. So, to find that, we take the margin of error, which we just found was 3, and divide by this inverse t. This inverse t is 1 plus confidence level divided by 2 for the area to the left. And there are n minus 1, which is 50 minus 1 is 49. That's degrees of freedom. So we just type this in on the calculator. We get approximately 1.49. And that's your standard error of the mean, or the standard deviation of the x bars, at least approximately. What's the sample standard deviation? Well, again, we're using this same formula here, and seeing that the standard deviation is square root of n times this standard error, right? S over square root of n is our standard error, or at least approximately. So S is at least approximately square root of n times the standard error, and so that works out to be approximately 10.556 hours. All right, here's another problem for you. A survey of the number of minutes students commute to university produced the following results: 10, 7, 25, 60, 55, 10, 20, 25, 18, and 12. Suppose that the population standard deviation of all such commutes is 10 minutes and that the individual commute times are approximately normal. Perform a test of hypothesis that the mean commute time is actually greater than 20 minutes. Return the appropriate statistics. Use alpha equals 10%. Construct a 90% confidence interval for the true mean commute time. Press pause now. Well, the mean commute time for a sample is 24.2 minutes. Performing a right-tailed z-test produces a test statistic of z star equals 1.328 and a p-value of 0.092. At the alpha equals 0.1 level, there is sufficient evidence to conclude that the mean commute time is more than 20 minutes. We're constructing a 90% confidence interval for the true mean. We're 90% confident that the true mean commute time for all university students is in interval 19.0 minutes to 29.4 minutes. Well, how do we find all that? Well, we just type in our data first in L1. So do stat, edit on a TI-84, put your cursor on L1, hit clear, and enter, clears out the list, then type in this data. Then we go to the z-tests, under Stat, and then left arrow to Tests. The Z-test is done from data here. The mu naught, hypothesized mu, is 20. Standard deviation, we're told, is 10. A list of our data is in L1 with frequency 1. We're looking for a bigger result, so it's a right-tailed test, so we choose greater than, and we calculate, and it calculates. There's our Z-star test statistic. There's the probability value P, and there's some other things that we could use there. Okay, the interval we could compute from the Z interval the same way. Choose the data. Most of the inputs are set the same. You just do confidence level. It's 0.9 this time. And it produces the interval. So we're 90% confident that the true mean is somewhere between, well, might as well call that 19 and 29.4. Notice both of these return the sample standard deviation and the sample size. A nurse recorded the number of days in recovery for a particular type of surgery as follows: 2, 1, 1, 2, 3, 3, 3, 5, 7, 5, 4. Perform a test hypothesis that the mean recovery time is greater than 2 days. Return the appropriate statistics and use an alpha as 5%. Construct a 95% confidence interval for the true mean recovery days, mean number of recovery days. Okay. Start by typing our data in L1. Of course, clear it out from whatever was in there before, or if you'd rather use a different list, you can. Just be sure to choose the right one over here. So type the data in L1. Use a t-test this time. Why t-test? Population standard deviation was not known, and we're testing for means. And it's one sample. So t-test. And by the way, the other thing we need to know is that the data is approximately normal. Okay? And that's what we need to do this. So we could do a normal probability plot for this to be sure that this is reasonable. For now, let's assume it is. We choose our data. The mu naught is 2 days. Our list is L1 for our data. Frequency 1, and we're testing to see that it's greater than this 0, mu 0, okay? And we run that, say calculate, it comes up with this screen. The alternative hypothesis is that mu is greater than 2. The t-star test statistic is 2.283. P-value is 0.02277. That's the most important part. The x-bar and the s are here, so on average, these people averaged about 3.27 repeating days, and with the standard deviation, the sample standard deviation of 1.85, let's say, and the n, the sample size, was 11. The t-interval that would go along with that would be use the t-interval program. Again, use data, same stuff as before. Choose the confidence level 0.95, calculate, and we get this. So we're 95% sure that the true amount of days that they have to recover is somewhere between 2.03 and 4.51. Okay, I think that'll do it for this video. Come back to the next one to finish up the problems on this homework, on this review set.